So we are asked, how in the world do we evaluate that integral? The bound 0 to infinity of 1 plus 2x, quantity in parentheses, e to the negative x dx. This one's a tricky one. This is an improper integral, and it requires a little bit of a harder integral to evaluate. So the first step of any improper integral is redefining our infinity as a variable of a. Or in this case, it could be b or any variable, but I just like to stick to a for most of these. So the limit as a approaches infinity for the integral of 0 to a of 1 plus 2x e to the negative x. This allows us to look at a value for infinity as, say, whatever the limit is as a approaches infinity, right? So pretty simple idea there. But now we just have to evaluate this integral, and this is an integration by parts. I know this because I can't just do u sub on it. I can't do any just normal integral of e to the negative x, and it looks like to me like, and the reason it's not u sub is because notice we, for if you take e to the x and we take the derivative of e to the x, what this will do is we take x prime e to the x. So we take the derivative, it's not going to be 2x. So I think of all the different things that we can do. It's not trig sub, it's not partial fractions. It's actually going to be just a simple old integration by parts. Now, I already know what u and v is, but you'd be wrong to say that u is e to the negative x, right? We want to reduce the power, and if you'll end up seeing if you use u as e to the negative x, you're going to increase powers, and it's just going to forever increase the power, and we don't want that. So u in this case is going to be 1 plus 2x, where du is equal to 2. V in this case is equal to the integral of e to the negative x. All right, which makes, with respect to x. So what is v really equal to? Well, we're going to take the integral here. We just know that's going to be e to the negative x. Okay? And you can prove this through the derivative. The derivative of negative x is negative 1. Bring that out front. That gets rid of the negative sign. And you'll get what we were integrating was. Okay, so that's pretty simple. Now we're going to re-plug in, we're not going to re-plug in. We're going to do the integration by parts formula. So it's u times v, negative e to the negative x, subtracted by the integral of v. So I'm going to bring out the negative to make it positive e to the negative x times du. So this is, we'll bring the 2 out front, dx. Hopefully you know how to do simple integration techniques, pulling things out in front. So what we'll do next is we'll distribute this. So we're going to say that negative e to the negative x plus minus 2x e to the negative x plus, and we're gonna, let me just make sure you guys can see. I like how every time I write stuff out, I like to slant it. It fucking sucks. So e to the negative x, the integral of that we said was negative e to the negative x. So this is going to be minus 2e to the negative x. Okay, so might be a little tricky here to see, but notice we have the like terms here. I'm going to go ahead and erase this up here to make room. So this is going to be, and you can see the like terms here, e to the negative x. So this is going to be negative 3 e to the negative x minus 2x e to the negative x. So I'll go ahead and erase my work here. Notice here they have a common factor, e to the x, and also a negative. So I kind of like to pull out the negative. So we're going to say negative 3 plus 2x, and we're also factoring out an e to the x, or e to the negative x. So factored, it looks like this. Hopefully you concur. Okie dokie, so let's now evaluate this as such. So the limit as a approaches 0 of a to 0. Okay, so not the hardest thing to do in the world, but it still requires a little bit of a thinking cap to hypothesize for. So let's evaluate it at a. So we're going to say the limit as a approaches infinity for -3 plus 2 of 2a over e to the a. Okay, so we're evaluating this limit now. So it should just be a simple limit problem. Notice that we're going to get -3 plus 2a, which is times infinity. So now let's evaluate this limit, e to the infinity. Okay, so e to the infinity is simply going to be 0. Or sorry, that's e, no, it's going to be infinity. 3 minus, or -3 plus 2 infinity is going to be infinity. So this is an infinity over infinity problem, which means we need L'Hopital's rule. So L'Hopital's rule says, okay, well, we have this here. We need to take the derivative. So we're going to take the derivative of the top here. So I'll go ahead and erase our normal evaluation to describe what the limit is. So the derivative of the top is 2. Derivative, and remember, L'Hopital's rule says if you have an indeterminate limit, infinity over 0 over 0, you can simply take the derivative of the top and the bottom, and that will give you what the limit is equal to at that point. And then e to the a is just e to the a. Does that make sense? Alrighty, so we can then go from here and simply evaluate 2 over e to the a, which is e to the infinity, which is infinity. 2 over infinity is 0. So our upper bound, that's equal to 0. We're going to subtract that by whatever we evaluate this to be at 0. So this is going to be -3 plus 2x in parentheses here, e to the negative x. So let's plug in 0. So let's make some simplifications. We have -3 stays, the 2 cancels out. E to the -0, anything to the 0th power is 1, so e, this cancels to 1, this cancels to 0. So we're left with -3 is what this evaluates to. We're going to then do our fundamental theorem of calculus, the upper limit minus the lower limit minus -3. We're going to get 0 minus -3 to be 3. And we're also asked if this limit is convergent or divergent. We did not find for this here, we did not find that as we approach infinity, it goes to infinity. That would be a divergent integral. But here we have a convergent integral. It converges at 3 because as the limit as a approaches infinity, we're going closer and closer to 0. So I hope you enjoyed this practice problem. If you did, please drop a like, subscribe, comment if you have any questions, and have a wonderful day.